All right, let's talk about math, but not the kind that gave you nightmares in school. We're going to dive into Keith Devlin's incredible book, Introduction to Mathematical Thinking, to completely reframe what math even is. Because, get this, it's not about boring problems. It's about unlocking a way of thinking that is, no joke, a real-world superpower. So, let's get into it. Have you ever had this experience? You totally crushed math in high school, you felt confident, and then you walk into a college math class and it feels like they're speaking a different language. If that sounds familiar, you are definitely not alone. And according to Devlin, there's a really good reason for that feeling. And this analogy just nails it. Think of school math as following a recipe. You're given steps, you follow them, and you get a result. Pretty straightforward. But true mathematical thinking, that's like being the chef who writes the cookbook. It's about understanding the why behind the ingredients so you can create something completely new. So here's our game plan. We're going to tackle that weird disconnect so many of us feel, see where it came from, and then redefine what math really is. And once we do that, we'll see how it all clicks together to become this incredible tool you can use, well, everywhere. First things first, let's talk about the great math disconnect. And here's the most important thing I want you to hear. If you felt that sudden, jarring shift from high school to college math, it's not you. It's not that you suddenly got bad at math. The entire system changed on you. Devlin has this perfect way of putting it. He says school math is basically like learning to drive a car. You learn the rules of the road, how to operate the vehicle, and how to get from point A to B. But college math? That's like popping the hood. It's about understanding how the engine works, knowing how to fix it, and maybe, just maybe, how to design a brand new one. So, how did this happen? Why the sudden shift from driving to engine design? Well, it all goes back to a quiet revolution that completely changed the field of mathematics itself. You see, for most of human history, being good at math meant you were good at calculation, at getting the right answer. But then, in the 1800s, thinkers like Dirichlet and Riemann started hitting problems that you couldn't just compute. They realized that the future of math wasn't just about doing. It was about understanding the deep, abstract concepts and the patterns that connect everything. And this quote from Devlin just says it all, doesn't it? The whole world of professional math pivoted from doing to thinking. The problem is, for the most part, our school curriculum never got the memo. It stayed focused on the doing, and that's where the disconnect was born. Okay, so if math isn't just calculation, what is it? This is where we get a much bigger and honestly, a much cooler definition of the whole subject. The modern way to think about math is this. It's the science of patterns. That's it. A mathematician's job is to hunt for patterns, describe them, and figure out how they work, whether those patterns are in numbers, in nature, in shapes, or even just in our minds. And patterns means basically everything. The patterns in numbers, that's arithmetic. Patterns of shape, that's geometry. You've got patterns of motion, which is calculus. Patterns of pure reasoning, which is logic. Even patterns of chance and luck, that's probability. Every branch of math is just the study of a different kind of pattern. Here's the real magic. By giving us a language to describe these patterns, math makes the invisible visible. I mean, think about an airplane. You can't see the force of lift. You can't see drag. They're invisible forces. But with math, we can see them, we can measure them, and we can build a giant metal tube that flies through the sky because of them. Okay, but if you're going to describe the invisible forces of the universe, you need a language that is ridiculously precise. This gets us to one of the most important rules of mathematical thinking. There is zero room for being misunderstood. For example, look at this headline. It's funny because it's ambiguous, right? We get the joke. We know they aren't literally climbing into the hole. But that's the thing about everyday language. We can get away with that. In math, where you're on the frontier of discovery, no way. And that's the fundamental difference. When we talk to each other, we use context and shared experience to fill in the blanks. But a mathematical proof has to be a fortress. Every single word has to have one and only one literal, precise meaning. It has to stand completely on its own. So how do they do it? How do mathematicians build these perfectly precise statements? Well, they use a small, powerful toolkit of logical building blocks. The first tool is the word and. It's simple. If you have a statement that says P and Q, it is only true if P is true and Q is true. If either one is false, the whole thing is false. Clean, simple, no gray area. Next up is or. Now pay attention here because this one's a little tricky. In math, P or Q is true if P is true, if Q is true,
or if both are true. It's what we call an inclusive or. As long as you've got at least one true part, the whole statement holds up.
All right, now for the one that really messes with people's heads, implies. A statement like, if P, then Q, is only false in one very specific scenario, when P is true, but Q turns out to be false. Now, here's the weird part. If your starting point, P, is false to begin with, the whole implication is considered true no matter what Q is. Think of it like a promise. If I say, if it rains, I'll bring an umbrella. The only way I lied is if it rains, the if part is true, and I don't bring my umbrella, the then part is false. If it doesn't rain, my promise is still good whether I brought an umbrella or not. See? It's not about cause and effect. It's all about logical consistency.
Okay, so patterns, precise language, weird logic rules. Why does any of this matter outside of a math class? Well, because when you put it all together, you unlock what is basically an analytic superpower. Devlin says there are two types of thinkers. A type 1 thinker is the recipe follower. They're great at solving problems that have a known procedure. But a type 2 thinker, they can walk up to a totally new, messy, real-world problem, see the hidden patterns, describe them with precision, and invent a brand new recipe to solve it. And in the world we live in, a world that changes by the second, companies aren't just looking for people who can follow the old cookbook. They are desperate for innovators. They need the people who can write the new recipes. That's the real value of mathematical thinking. So look, this isn't just about getting better at algebra. It's about achieving a new level of clarity in everything you do. You've just learned the very first rule. So I'll leave you with this question. What part of your world are you going to start seeing with more precision now?